All right. Good afternoon, everyone. Let's start. So in the last lecture, we introduced the basic ideas of linear models with arbitrary nonlinear basis. Again, we want to emphasize that although we kind of maintain a high-level linear structure, but you're free or you're flexible, you can flexibly introduce all kinds of nonlinear bases. That means you can do some nonlinear feature transformation and then apply this linear structure. That means our linear model does not necessarily mean you just capture the linear relationship between input and output. Actually, our large family of models can be categorized as linear models, even including the commonly used feed-forward neural networks. Right? So we introduced the idea of linear models for regression, linear model for classification. We talk about logistic regression, multi-class logistic regression, and probability regression, ordinal regression, and so on. Right? And we talk about if we do MLE estimate of logistic regression, we can use the more effective optimization technique called Newton-Raphson's update. Right? So we'll derive the form for the updates. It resembles like each step you're solving a least mean square problem. So that's why it's called iterative. It is also called iterative related least square method. Right? So to wrap up, we now introduce the idea of generalized linear models. So what does it mean? It just means we consider to impose this linear structure in the exponential family. As we mentioned before, exponential family takes a critical role in the probabilistic modeling. It actually includes many commonly used distributions. So we want to come out with some like a general definition of linear models. Here, we're gonna look at exponential family. Right? So here T is our data, our observations. The eta, as we mentioned before, right? Eta actually is a natural parameter. And the likelihood or the distribution of the data is modeled as exponential family. That means the distribution looks like this, right? E to the power of the inner product between the natural parameter and the observed random variable t subtracted by g of lambda. G of lambda is a log normalizer. And here we just, for simplicity, we just use t, but in a more general sense, you can assume you apply any transformation or any function to get the sufficient statistics. It should be a function of t in the most general sense. Right? And we talk about the property of exponential family. That is, if we take the expectation of the random variable t, right, or the sufficient statistics of t, right? But here we just use sufficient statistic to be t itself. Given its natural parameter, we denote this expectation by y. We know that this expectation essentially is the gradient of the log normalizer with respect to the natural parameters eta. This is a well-known property of the exponential family. We have discussed it before. And in our homework 1, if you can recall, we also asked you to further prove that if I take the gradient again, it will give you the covariance of t. So from this result itself, we can see that there actually is a mapping between the expectation and the natural parameters. So in other words, if you want to determine the parameters of this distribution, we'll actually have two types of representations. First, we can represent this distribution in terms of natural parameters lambda. So you're going to have this form. But you can also determine the distribution by the mean of the distribution or by the expectation distribution. So then y here is usually referred to as expectation parameters. In fact, the most commonly used distribution are parameterized by their expectation parameters rather than the natural parameters. So, I mean, in my personal opinion, they should switch the name. The expectation parameter should be called the natural parameter. Natural parameter should be called other parameters. Anyway, for example, the Gaussian distribution. When we talk about Gaussian distribution, we always ask, what is the mean? What is covariance, right? So if you, let me write something to be more clear, right? So when we write a Gaussian distribution, right, our first reaction will be asking, what is the mu? What is the variance, right? Mean and covariance. So mu obviously is the expectation of t itself, right? But here, what about the v, right? The variance. So if you just made some simple addition, right? V times mu square is essentially expectation of t squared, right? So it's actually another expectation. So if you write down the exponential form of this Gaussian distribution, we know that the sufficient statistics, let me use UT, right, actually consists of two components. One is t itself, the other actually is t squared, right? So actually, t and t squared, their expectation are mu and v plus mu squared, respectively. So when we, in the most of the cases, when we talk about Gaussian distribution, we're actually asking what are the expectation for t and t squared. That's our, I mean, everyone when they learn the Gaussian distribution, right, that's how we parameterize Gaussian distribution. And rarely, we're going to talk about how to obtain a natural parameter for Gaussian distribution. So although we talk about it in our class, but if we don't discuss it, maybe rarely people will be aware there is another type of parameterization. Okay. So that means for distribution in an exponential family, or a convenient unified parameterization is to introduce a so-called natural parameter. But at the same time, according to the practical usage, they are also parameterized by the mean parameters or expectation parameters. Right? And there is a mapping between the natural parameters and expectation parameters. And their relationship is reflected in this result. So now, come to the model. In linear models, right, we want to assume some linear structure in terms of model parameterization. Following our common custom, or our custom which make us feel comfortable, right? We often parameterize the expectation parameters. We also assume we can impose a linear structure in the expectation parameters. So that is, we can assume, okay, our output y, our mean parameters y is some function of an inner product between the model parameters w and the sufficient statistics. And of course, you're free to choose f. Now, if we choose f to be a specific form, that is the inverse mapping between the natural parameters and the mean parameters, this formulation is called a generalized linear models. So in other words, generalized linear models doesn't mean really generalized linear models. It just means, okay, if you define your expectation parameters in this form, and this transformation f is taken as the inverse mapping between the natural parameter and expectation parameters, then it's called generalized linear models. Then let's see what happens if we choose this f equals to psi inverse? Right? So we know that eta, the natural parameters, is represented by psi of y. Right? So now, if we plug in the modeling of y in terms of this, right, w transpose phi x, that means y is replaced by this guy, right, psi inverse, because I have to take psi inverse w transpose phi x. So you know that to get eta in the outer level, we need to apply this transformation psi. So psi transform with psi inverse, so it just cancel out. The result tells us through choosing psi inverse as f, we got our model of natural parameters outright as a linear structure, w transpose phi x. Right? And f inverse is the called link function. So you might have seen some literature in statistical learning. They say, okay, we're going to use some linear models or nonlinear models, then throw some link function to the outcome. So the link function comes from here.
Psi inverse or f inverse?
Psi, f inverse. That is psi.
Psi.
Yes. Yeah. So basically, the link is actually link the expectation modeling, the linear structure in the expectation modeling to the natural parameter. This is called link function. Right? So it links expectation to the natural parameter. Yeah, that's the slide time set. That's it. That's this concept. Although in practice, you rarely use this generalized linear form for your probabilistic modeling, because you're always dealing with particular application, and you want to deal with this particular application. But this more general framework tells you how in this family of distributions we model, we build out our linear models. And on the other side, you can simply view in the generalized linear models that we essentially impose a linear structure to the natural parameters. Okay. So now let us take a look at the estimation of generalized linear models. Again, here we just look at the MLE estimation regarding the Bayesian inference, like how do we estimate posterior distribution of the model parameters. We're going to talk about them later, because right now we just talk about the model. And for the inference, there are a family of techniques we're going to go through. So suppose we're given n training input and output pairs, right? And the negative log likelihood, well, we assume this training data are IID, right? It's just the summation of the log likelihood of each training points. So because this is an exponential family, right? If you take logarithm, it will give you this form, right? So this is the natural parameters for the nth example, dot product, or if it is just scalar, you just multiply with the observation T of n and subtracted by the log normalizer. So if we take the gradient with respect to the negative log likelihood, it will give you this. So partial eta n over partial w. Remember, eta n is a linear model, right? So it's w transpose phi x n. And then subtracted by the gradient of a log normalizer. Here we can use the chain rule to calculate the gradient. So after some manipulation, it is easy to see that the gradient of the negative log likelihood is a summation of a feature vector or mapped feature vector times the difference between the observation Tn and Yn. And Yn is the expectation. Remember, Yn is, as our notation, is the gradient of the log normalizer with respect to the natural parameters, which is essentially the expectation. So there's an interesting structure in the gradient of the log likelihood. So you just add up the difference between the observation and the expectation under your model, and then multiply with the future vector. So this is called prediction error, right? Because when you make a prediction, you usually just use the prediction of your model, the expectation of your model output, make a prediction. You will, this can be the on average the best prediction. And if you can check back the gradient structure for linear regression and logistic regression, you see that they kind of share the same structure. And this is reasonable because both linear regression and logistic regression are just instances of exponential family generalized linear models. Okay, any questions so far regarding linear models, generalized linear models, and all those concepts? Can I say what distribution?
So for any data distribution, if I can convert it into an exponential form, then it's a linear model, right? That's what.
Okay, you're asking for any distribution with more data that converges to some linear models or exponential family?
If it converges to exponential family, then it's a linear model, right?
No, not necessary. Again, I mean, exponential family is just a family of distributions. It's hard to claim that for some data distribution, they're going to converge to this family. So there are a lot of like distributions. Again, this is a whole space. And exponential family is a subset of those distributions which have nice properties. And also the elements, I mean, the members of the exponential family are commonly used. That's why people pick them up and focus on them. But that does not necessarily mean all the other distributions can be replaced by the members in the exponential family. Like take an analogy like a convex function. Why people study so much on convex function? Because they are easy. They have nice properties. We can leverage a lot of them. And in many cases, we try to approximate the hard distribution, the hard function by convex functions. But they can definitely not represent all the functions. Any other question? Okay, great. So to wrap up, what you should know about linear modeling and generalized linear models. So be familiar with the concept called design matrix. So design matrix is like data matrix. Suppose you have n data points, then design matrix should have n rows, and each row corresponds to the mapped feature vector, right? Through some nonlinear basis. And this term is often is quite often in statistical learning literature. So they assume you know that by default. And how to obtain MLE for linear regression, and how to obtain posterior and predicted distribution for linear regression, because we assume, okay, if you have a Gaussian probability, you have a Gaussian likelihood, it is easy to derive the posterior distribution and predictive distribution. But for classification case, it's not that easy. That's why in the classification case, we first just introduced how can we perform MLE. When we talk about how to do the posterior inference, we need to leverage some approximate inference method, like variational inference, like Laplace approximation, like Markov-Chain Monte Carlo sampling. And whereas empirical base and type 2 MLE, as we discussed, associated with our structure of log model evidence, we know that when we maximize log evidence, we're actually finding a best trade-off between the model complexity and data fitting. And Newton-Raphson methods for logistic regression. What is probability regression? What is the equivalent augmented model? We talk about why probability regression is is also very popular, partly because it's more favorable for Bayesian inference, because you can assume there is some latent intermediate random variable, first sample from Gaussian, and then generate the output from some step function. And you see that in the inference, it will be a lot easier. And what is generalized linear models, what is link function, and what is general form of the gradient. Okay, so we're gonna stop here. So we're gonna talk about another family of probabilistic models. Sorry, give me a few seconds to enlarge this panel. All right. Okay. So from today, we're going to spend quite a few lectures introducing a family of very important probabilistic models. It's called probabilistic graphic models. It's being perhaps the most important topic in probabilistic learning for a long time. Right now, maybe people put a lot of attention, focus on deep models. And deep learning is all kind of architectures like transformers, those things. But in a more general sense, they all belong to a particular type of graphical models. Okay. So what is, in general, what does it mean for graphic models? So as the name suggested, they're going to use the graphical structure to represent probabilistic models. So it is a marriage between a graph theory and probability theory. More specifically, we're going to use graphs to represent probabilistic models and facilitate inference. And as to how the probability, the joint distribution is encoded as a graph structure, we're going to talk about in a minute. But just to give an overview, the graphical structure reflects the conditional independency of the model. So because everything is reviewed from the graphic structure, so the graphic models are usually intuitive, convenient, and expressive for modeling. And also, because the graphic structure reflects some kind of simplification about the joint probability, so the inference will rely on the graphic structure to make it more efficient and convenient. So it is easy to implement, apply, analyze, improve. And finally, I just want to emphasize neural networks are instances of graphic models. So here is our outline for this topic. We're going to first introduce directed graphic models, which are also called Bayesian networks. So the inventor of the Bayesian networks is Julia Poor, who has found the tuning work partly, I think mostly because of the probabilistic modeling and probabilistic inference, and partly because of causal inference. But I think causal inference is not as influential as graphic models. As causal inference right now, the application is still kind of limited. But the Bayesian networks are indeed very widely used. Even if you I'm taking some artificial intelligence course, like in my undergrad school, when I took that course, they told me that they use Bayesian networks to build some expert system, like some MIT group. They build up a medical system called QMRT. It's two-layer Bayesian networks, which can diagnose a type of disease. It's said to be very accurate. It is be even better than some physicians, practice physicians, and also the Bayesian networks, and also the, I mean, in that age they call it expert system, are widely used in like device manufacturing, and like even the diagnosis of many malfunctioning in astronautics systems. So we're going to introduce graphical representation, conditional independence, and deseparation and baseball algorithm. And later we'll talk about what's them, why we should learn about them, and we'll introduce the concept called Markov blanket. And then we'll talk about undirected graphic model, which is usually referred to as Markov random field. And you see that Markov random field actually is simpler and more convenient than Bayesian networks. The conditional independence is really easy to derive. And we're going to talk about how do we make a connection between Bayesian networks and Markov random fields. And finally, we'll introduce some general inference algorithms on graphic models. We'll introduce the so-called factor graphs, sum product algorithm, and max product max sum algorithms. So those inference algorithms are exact inference algorithms, meaning that I don't make any approximation. And if the graphical structure itself is good, like it is chain structure or tree structure, you can do the inference very efficiently. But later, when the graph structure is not that good, like it is not just a tree, right? So you cannot guarantee the inference is that, and then those algorithms become some approximate algorithm, which is usually called message passing algorithm. And message passing can give you some from optimization point of view, it is essentially a fixed point iteration. It can, if it converges to some stationary point. Actually, it's a saddle point for some energy function defined on that graph. It is kind of like very interesting. So it's widely studied by computer scientists and also physicists, and also electrical engineering people. Okay, so now let us first introduce Bayesian networks. So to motivate Bayesian networks, let us revisit Bayes' theorem. So we know that Bayes' theorem tells us how to compute the posterior distribution or conditional distribution, right? So if we want to compute the distribution of x2 given x1, we just divide the joint distribution of x1 and x2 by the marginal distribution of x1, right? So if you condition on x1, you're going to divide the marginal distribution of x1. Right? And then if you multiply the denominator to the left-hand side, you can get your joint distribution of x1 and x2 can be decomposed as the product of the marginal distribution times the conditional distribution of x2 given x1. Right? And we can extend this result for n random variables. We can apply this decomposition. We know that the joint distribution can be written as the marginal distribution of x1. Then conditional x1, the distribution of x2. Then conditional x1, x2, the distribution of x3. You can continue until you multiply the conditional distribution of xn given x1 to xn minus 1. Okay. That's the Bayes rule. That's what Bayes rule reflects from another point of view. It actually tells you the joint probability can be decomposed into a series of product, like a series of conditional distributions. And this decomposition actually defines a sampling procedure. Okay. If you, according to this joint distribution, how do you sample the values of x1, x2 to xn?
Has some at first x1,
Mm-hmm.
then using the probability condition for x1.
Yes, exactly. Okay. So following this decomposition structure, actually we can first sample x1, right? And given the value of x1, we sample x2. And given the value of x1, x2, we sample x3. Continue until we sample xn, given x1, the values of x1 to xn minus 1. So you can see that as long as you define a joint distribution across all the random variables of interest, you essentially defines a sampling procedure to get values of those random variables of interest. And as to how you generate or how you sample them, it is determined by the decomposition structure within this joint distribution, right? That's a very important viewpoint, because later we see that actually when you construct the Bayesian model, a probabilistic model, we always intuitively come out a sampling procedure. How we sample x1, how we sample x2, how we sample x3, and then until, right? And once you figure out this whole sampling procedure, you will then be able to build up the model and write down the joint distribution. So now, for a concrete case, consider a probabilistic model over 3 random variables, A and B and C. So we can write down its joint probability as the marginal distribution of A, and then the conditional probability of B given A, and the conditional probability of C given A and B. Of course, there are multiple ways to decompose this joint probability. Right? Let's just choose an arbitrary one, starting from A, and then given A, sample B, and given A and B, sample C. Okay? So given this structure, a natural question would be, can we use the graph to represent this joint probability? So we can denote each variable of interest, like A and B and C, by the nodes in a graph. Like we have 3 nodes, A and B and C, or 3 vertices in this graph. And then if we have a conditional probability, say P of B given A, we're going to make a connection from the condition part to the random variable. So if we connect A to B, it just indicates there's a conditional probability P of B given A. So the target node is the random variable in this distribution. And the source node or parent node is the condition part. And if you condition on nothing, then it just means that there's no incoming edges, or there's no edges pointed to. Like in here will be A, right? And then if we look at the conditional probability of C given A and B, because it's conditional on 2 nodes A and B, it has 2 parents. Right? So you can say there are 2 coming edges to C. One is from A, the other from B. So in this way, we can define a graph to represent the joint probability. And without, any specification of the form of this conditional distributions or marginal distributions, through this graph structure, we can immediately write down the joint distribution form, right? So for A, well, you don't have any incoming edges or parents, so you just write down the marginal distribution of A. And then if you look at B, because there's one incoming edge, right? That means it has one parent from A, so you got a conditional probability of B given A. And then you look at C, well, it has two parents, so it's conditional on A and B. That's our notion of the Bayesian networks. So I'm going to repeat this rule again. So given a joint probability, we use a node to represent each random variable in this joint probability. So for each conditional distribution in this joint probability, which in general has the form P of A given B1 to Bm. Of course, M can be 0. We then add an edge from each condition random variable to A. So the random variables in the condition parts are represented as the parents. If no conditional parts in this term in the probability, right, the node has no parents. Okay, does it sound reasonable for everyone? It's just a simple rule to, to draw a graph to represent the decomposition structure of the joint probability. So, oh yeah, of course. If yeah, that's a very good question, because later we're going to talk about how we simplify the structure. But here, yeah, if, for example, if you assume A and B are independent, right? Something like that. Then how do you construct a graph? You can see that A and B, they both have no condition part, right? That means they have no parents, right? What you see, in this conditional distribution, they have two parents, so your graph will be something like that. And essentially, design Bayesian networks is the art to reduce the edges. Okay, now we can take a look at this example. A similarly more complex example, we have 7 random variables, x1 to x7. So here is the joint probability. So we can see that x1, x2, and x3, they don't have any conditional part, or they condition on empty. Right? So when you draw their nodes, right, you see their x1, x2, and x3, they don't have the incoming edges. They don't have parents. And then given an x4, its distribution is conditioned on x1, x2, x3. That means when you draw x4, you should connect x1, x2, and x3 to x4. So it has 3 parents. Then if you take a look at like x5, it is conditioned on x1, x3, right? So you can see that there are incoming edges from x1, x3. And similarly, for x6, it is conditioned on x4 only, right? So it has only 1 parent. Right? For x7 is conditioned on x4 and x5. Right? So it has 2 parents, x4 and x5. So then we can come out, we can finish our structure of Bayesian network representation. Yeah, there are different graphs. That's also a good point, because you might have different way to decompose your joint distribution, and it will correspond to different graphs.
So simply you can say that for any random variable, the probability given its parents is any random variable given its parents is independent from the other variables.
No, we cannot see that.
Yes, just when you have its parents, it seems that you from the others.
Yeah, those edges exhibit the decomposition structure in this joint distribution. That's for sure. But if you want to talk about conditional independence, by just looking at those edges are not enough. We're going to talk about how do we generally, what kind of rules can we generally use to conclude if one set of variables are conditionally independent on another set of random variables. There are some several basic structures which show some conditional independence, and then you're going to leverage some algorithms, which is called baseball algorithms to verify it. But basically, from the structure itself, what you can tell is that, okay, it can tell us how do we sample these 7 random variables sequentially. Okay. You can see that, okay, x1, x2, x3, right? They're conditional on nothing. So we can first sample x1, x2, x3. Then condition on their values, we can sample x4, x5, and x6, and then x7. From the from the first side of structure, we should be able to tell how we're going to generate instances or samples of those random variables. Does it make sense? Yeah. I would say, given specific Bayesian network structure, you can write down a joint probability. And associated with this graph structure, this form is unique, but it's not vice versa, meaning that given joint probability, it might correspond to 2 graphs, right? If you take our 3 random variables case, you can write it as a P of A times P of B given A, P of C given A and B. It corresponds 1 graph. You can write it on P of B times P of C given B times P of A given B and C. This is definitely another graph. And they have different structures, but they all correspond to the same joint probability. Yes. Yes. So we name this representation as a Bayesian network. And one important fact is Bayesian networks must be directed acyclic graphs. Why? Means there shouldn't be any cycle in a Bayesian network. Yeah, can you be a little bit more straightforward? You have a yes. Let me put it in even more explicit, right? So consider that you have this cyclic directed graph, right? What does it mean? As we just mentioned, right? Any Bayesian network defines a probabilistic sampling procedure, right? To sample those random variables. Right? So if you use this, it just means, okay, you're going to sample A given C, but C is now yet not known, right? And then given B, you sample given B, you sample A, given A, you sample B, given B, you sample C, and given C, you sample A again. You cannot sample with this cycle. Actually, you cannot define a procedure to sample A and B and C, right? Because if you want to sample A, you must know C. However, C is yet sample, right? Because if you want to sample C, you need to know B, right? And then if you want to know sample B, you need to know A again. So it won't give you a valid procedure to generate the samples for those random variables. Yeah, I mean, only if you cut this cycle, it can give you a value for this model, value-based model. Otherwise, it's not valid. Yeah, I mean, you can cut any edge to eliminate that cycle, and then make the whole structure as a directed acyclic graph, and that would be a valid. We just explain why this cannot be viewed as a valid probabilistic model. Yeah, of course. Like that means like A and B and C, right? That just means A and B and C are independent. The joint probability is just the product of their marginal probabilities. Yeah. Another question? Okay, great. So yeah, that's just explanation. A cycle means one variable is sampled, appears in the conditional part, to sample other variables, and then sample again. This violates the Bayes rule. So now let us use Bayesian network to represent some more practical models, right? Like polynomial regression. So if you write down the joint probability for a polynomial regression model, right? Suppose this bolded T is just consists of n observations. Right? So you have a prior over the weight vector W. Then given the W, we're gonna sample each output Tn given some training input. Right? So obviously, to create such a network, you're gonna have a node which denotes W, right? And because W is only some from prior, it is not conditional on any other things, so there's no parents, right? Then given W, you sample each output T1 to Tn. Well, because there could be many, you just use the dot to avoid drawing all the circles. However, in practice, our Bayesian models can be quite complicated. You have many terms, and you have but you also have like many duplicated components. Like in our case here, we know that for each component, they actually corresponds to the same form of likelihood. Right? Seems that we don't need to replicate these components again and again. And also, the prior itself might not be conditioned on some random variables, but might be conditioned on some deterministic parameters, like hyperparameters. And how can we make our network to be more specific and succinct? In our take our linear regression as an example again. Right? So we know that the prior of W, which is Gaussian prior, but the wideness of the prior is determined by this hyperparameter alpha. Right? Let us assume alpha is just some fixed constant rather than random variable. And also, given W and given each input observation xn, and the output Tn is sampled from a Gaussian distribution, but is determined by some noise variance sigma squared. Right? We assume this noise variance is known, it's fixed, it's not another random variable. And how can we represent them? So here is a more succinct way to represent the whole joint probability. Right? So we use small solid nodes to represent those deterministic parameters and uninterested observations, like xn, because xn is given. We're not trying to estimate xn itself. Xn is just some constant. So here it will include the prior parameters alpha and the noise variance sigma square, and also each input xn. And then we use big empty nodes to represent latent random variables. And here we're going to assume W is unknown, right? It's latent random variables, and also the output given the input is unknown. So we use this big empty circles to represent them. And if one component appears multiple times, like suppose we have n such kind of random variables, we can draw a plate outside of this component, and then use a label n to denote this is this component will replicate for big N times, but each time, because each parameter xn and also each random variable are Tn, so they vary according to n. And then through this way, we can succinctly represent whole joint probability. Any question? It's just a notion to more conveniently draw our Bayesian network. Okay. If you look at this, you should be able to write down the joint probability. We know, okay, for the W, we must have some prior, right? Given alpha, and alpha, we know, okay, alpha here, we just assume it is a knowing fixed constant. And then given this plate, I know, okay, there must be the same component, the component of the same form replicate n times. Right? So we're going to write down the product. Right? And inside each plate, to instantiate each component, okay, we just look at, okay, this condition W because its parent is W, and the random variable is Tn, is given W, and also given Xn, second parent, and also determined by a third constant parameter. It's not constant parameter, it's actually some fixed constant, same as well. Any question? Oh, this is really straightforward. I just want to avoid confusion, any confusion about notations. Okay, so now for the training process, we know that when we collect a bunch of training inputs and outputs, in our case, it will be pairs of Xn and Tn, right? In this case, the Tn, the output, has already been observed. So we use shaded nodes to denote the observed latent variables. That means our remaining task would be just estimate distribution of W, because right now only W is unobserved. But you want to infer W given these observed values Tn and also other constants. Okay, so now we have introduced the general definition of Bayesian networks. And here we want to emphasize that the network structure is determined by the factorization of the joint probability or the decomposition of joint probability. Right? How do you write down your joint probability in terms of product of a bunch of conditional probabilities, the marginal probabilities? Right? So different factorization leads to different structures, as we just showed. Right? So even for the same joint probability, if you have two factorizations, it might correspond to two graphs. So don't be surprised that they have multiple representations. Right? So equivalent models may have different structures. So the second thing I think is even more and even more critical. So how to design the factorization of the joint probability is the key to the probabilistic model. Right? So, if you just write down, okay, I use the base rule, right? I just decompose my joint distribution, use the full base formula. Actually, is not informative at all, right? Because for any joint distribution, you can decompose in that way, right? P of x1 times P of x2 given x1, P of x3 given x1, x2, and so on. And in fact, the value of your Bayesian network modeling is how do you simplify this structure. and reflected in a graphic structure. Like if you use full base formula, you can imagine it's a full graph. X1 connects to X1, X1 connects to X2, right? X3 is connected by X1, X2. X4 is connected by X1, X2, X3. Right? This is a full graph. Right? But if you make your Bayesian network more valuable, more meaningful, you're gonna simplify the structure. You're gonna delete some kind of edges in this network structure to make your inference easier. And also this deletion of those extra edges reflect your own prior knowledge or domain knowledge or your beliefs about this model structure. So that is actually the key for the Bayesian network model. So for probabilistic modeling, we nearly always use domain knowledge to simplify the joint probability, right, which can be reflected by the network structure. If you throw a bunch of edges, you take a look at B, right, C, D. That's full Bayesian formula, right? If you just decompose accordingly. That's actually not very useful. And if you can use some kind of domain knowledge with some prior knowledge, like you can cut off some edges from here, that is more valuable. That is our goal to design a Bayesian network, because doing so can simplify the model estimation and facilitate inference and make it more accurate. And the simplification is called a conditional independence. Why? Like, imagine if you're doing, let me index those variables, xn, x1 to x2, x3. Okay. Suppose you use full Bayesian formula, right? So when we go to x4, we should condition on x1, x2, x3, right? That means we have to connect x1, x2, x3 to x4. You have 3 edges. But now if we want to simplify it, we want to x1, x2, x3, x4. We want to make some kind of simplification. That means we want to cut some edges. So that means we're gonna assume this conditional distribution is equal to x1 and x2. Right? You cut edge connecting x2 to x4. So this tells us conditional x1, x3, x2 are independent to x2. Right? That's why we say this simplification is called conditional independence.
One question is related to my third question. So we can say that any random variable, given its parents, is independent from its ancestors.
Given its parents is independent by, I would say, predecessors, or yeah, that's an immediate conclusion. But there are a lot more from that. Okay. Yeah. Later we'll talk about how do we find all possible conditional independence from the structure, not only from this this structure. I mean, from this intermediate design. I mean, how each node is connected to its parents. We can see some kind of intermediate conditional independence for sure. But beyond that, there can be many other conditional independence. So this it's not to, we're going to talk about the general way to check if any conditional independence holds. Okay, but first let us look at the benefit of this simplification. We use the linear Gaussian model as an example. So suppose we have an n multivariate Gaussian variables. Right? If we use full base formula, meaning that we do not make any assumption, as we just mentioned, right? So we decompose this joint probability by P of x1, P of x2 given x1, P of xn given all its previous and the variables until P of xn given x1 to xn minus 1, right? And if we assume, I mean, this is a linear Gaussian model, it's basically say the mean is a linear combination of the condition and the variables and the variance, right? So if we build up network structure, it is fully connected work, and the parameters that needs us to meet to estimate will be the scale of n squared, right? Because for random variable n, if you want to identify its conditional distribution, you're gonna use ON parameters, right? And then if you go over x1 to x big N, you're gonna have a ON squared parameters. That's definitely quite complicated. If your n equals to 100, you're gonna use 10,000 parameters. What? YON2? Okay, so for any conditional distribution P of xn, small n, conditional x1 to xn minus 1, right? So you need to know the coefficients for each condition variables. Right? What? Yeah, it's mean. So linear Gaussian just means, okay, I'm gonna use a linear combination of the conditional part to model its mean. So you see, mean plus variance, it will take n parameters. And you're going from x1, x2 to x big N. So you sum up together, you will give this big O n squared number of parameters. Any question? Okay. Now, if we simplify structure, I mean, again, if we just construct Bayesian neural network, this is a full Bayes formula, right? You see that this will be a fully connected network, right? If we do this x4, we're going to have a x1, x2, x3, oh, here, and you keep going, right? There are many edges. Right? So now I want to simplify the structure, which is the No, it's not. Yeah, because x4 is conditioned on x1, x2, and x3. Right? So you have edges from all x1, x2, x3 to x4. Yeah, that's something I'm going to talk about. If you assume this conditional distribution is equal to x4 given x3 only, well then x4 is independent to x1, x2 given x3. That's conditional independence. And they are going to be reflected by the simplified structure. So if we just assume a chain structure in this sequence of random variables, right? We don't add additional edges from all the previous nodes. You can see that the structure is much more simplified, right? And then we define our conditional probability in this way. Again, it is a linear Gaussian model. So xi conditional its parent is xi times a linear combination of its parent plus some bias term and vi. Right? So now, because each node only has one parent, right? So that means each conditional distribution is only parameterized by O1 parameters. So I have n variables, then your total number of parameters is On. It's linear to the number of variables. So you can see the model structure is much reduced and simplified. And in fact, this is a very effective simplification in many applications. For example, Markov chain. Right? So people, when are modeling many sequence models, right? They just assume, okay, in step K, the random variable is only dependent on the step T minus 1, rather than all steps 1 to T. Although the latter might be more comprehensive, but in most cases, it's just not that useful, and also brings a lot of more computational burdens. Okay, in general, the simplification of the Bayes rule or the full Bayes formula reflects our ideas, tricks, and knowledge in probabilistic modeling. Again, how is the simplification reflected? It's called conditional independence. So, what is conditional independence? Although everybody should feel easy, right? Conditional independence, but here we want to give some kind of formal definition, because we're going to talk about how we conclude conditional independence, or we check the conditional independence given a network structure. Right? So consider a probabilistic model over 3 random variables, A, B, and C. Right? A is conditionally independent of B given C if the conditional probability of A given B and C is equal to the conditional probability of A only given C. Then we say A is independent of B given C. Another popular notation is this. Right? So this perpendicular notation is used to indicate the independence in the probabilistic world. And as to why, actually, we have mentioned before, right? We can use this to denote independence. Conditional independence, you can also use this, right? So the joint conditional independence. The joint conditional probability is the product of the marginal conditional probability. So you can, from this, you can easily derive this. So when we, as we just mentioned, right, when we reduce the edges from a fully connected Bayesian network, we're actually introducing conditional independence. Right? So if we use full Bayes formula to decompose the joint probability of A and B and C, it will be P of C times P of B given C, P of A given B and C. Right? So that will be some edges like that, right? You just look at this decomposition. P of C and P of B given C, and P of A given B and C. And A has 2 parents, C and B. But now, if you choose this decomposition structure, that we preserve P of C and P of B given C, but now the third term, we use P of A given C. We're gonna cut this edge. Right? And cutting this edge will tell us, given C, A and B are independent. But of course, as we just mentioned before, this is just for simple network. You might just with your eyes, you can see the conditional independence. But when the network is very large, it's hard to just point out every conditional independence. We need a general principle. And in general, however, when we design a Bayesian network, we usually don't list a bunch of conditional independence and try to write down the joint probability structure. That is kind of counterintuitive. Instead, we always consider a sampling or generation process to get the values of those random variables. Like suppose I have a bunch of random variables, x1, x2, x3, x4. Okay, I might believe, okay, I'm gonna sample x1 from some prior distribution. And then given x1, we're gonna sample x2 and x3. And given x2 and x3, we're gonna sample x4. Go on until we sample all the random variables of interest. And once we figure out this probabilistic sampling procedure, we can write down the joint probability structure, right? Which is multiplication of those marginal distribution and conditional distributions. And through this product, we can draw our Bayesian network. Then the question will be, okay, underlying this whole fancy sampling procedure in your mind, what kind of conditional independence is reflected? In other words, for a complex Bayesian network, given arbitrary non-overlapping sets of nodes A and B and C, how do we test the conditional independence? A, B, and C are three sets of random variables. They are not overlapping. If it is overlapping, of course, it's not conditional independence. If they are not overlapping, then how can we tell if given C, the set of random variables A are independent to the set of random variables B? And this is important to analyze your model. And what is the underlying properties of the model? However, to answer this question is not straightforward. It's not that easy. And actually, one of major contribution of Professor Julia Purr, is to develop a very simple yet effective algorithm to answer this question for arbitrary A, B, and C. Okay, so we're going to talk about how to do that, right? So we'll summarize several basic cases, which can tell you in three basic structures in what cases those random variables are conditionally independent, in which cases those random variables are not conditionally independent. And then we're going to leverage those basic structures and put them in kind of a searching procedure, and to test every possible paths and then give the final conclusion. So this is called a D-separation. So the first basic case has the structure of this. Oh, by the way, those structures all include the three random variables, or a bit more for the third case. Right? So the first basic structure is called tail-to-tail structure. Why is it called tail-to-tail structure? So it just says, okay, if we want to connect A to B through an intermediate random variable C, so you can see that okay, your path will first go to a tail, go through a tail of this edge from C to A, right? And when you pass C again, you see another tail. That's why it's called tail-to-tail. So for this tail-to-tail structure, we conclude that if condition on nothing and A or B are dependent, is not independent. However, if condition on C, A and B are independent. So how can we see this point? So for the first case, we can start from the first case. Again, if we want to look at if A and B condition on nothing, that means they're joint probability A and B. If A and B are independent, that means we must find a structure which can decompose the joint probability A and B equals to P of A times P of B, right? Now, from the definition of this, from the Bayesian network, we know that first, the joint distribution of A and B is a marginalization of the joint distribution of A and B and C, right? And then according to our network structure, we know this joint probability is decomposed of P of C times P of A given C times P of B given C, and then integral with C, right? So you can see that actually any choice of C is in both conditional probability A given C and conditional probability of B given C. So actually C couples these two components. Right? And then if you do the integral, if you integral C, and these components are tightly coupled. So they won't give you a factorization structure like something like FA and G and B, right? That's why we can now conclude your joint probability of A and B will be factorized by two terms. One term contains A only, one term contains B only, and then that means in general A and B are not independent. Does it make sense? Because C is in both conditional probabilities, right? And now you integrate over C. So actually, it kind of like tied these two terms together through this integral operation. And you cannot expect that finally the result will be a factor of A only and a factor of B only, because they're connected. But now, if a C is given, C is condition arm. I mean, C is a knowing value. Let's see what happens. If C is a knowing value, if we want to take a look at the conditional probability, right? If you want to say A and B are independent given C, it's just to check if this is equals to P of A given C times P of B given C, right? That's the definition of conditional independence. So you can check, right? So this guy equals to the joint probability of A, B, and C divided by the marginal probability of C, right? So according to the network structure again, right, we just copy this here. So it's P of C times P of A given C times P of B given C divided P of C, right? So we cancel it out, it is exactly right hand side. So that's why we can conclude that, okay, if C is given, well, A and B are conditional independent to each other. That's the first basic structure. Right? We can conclude that if you happen to meet this network, tail-to-tail network, right? Given the intermediate variable C, A and B are independent. However, if you condition on nothing, that means you have to marginalize C. They are not independent. A second basic case is called head-to-tail. This is very similar to the structure of tail-to-tail, but we can see that A goes to C, right? And now C goes to B. It's not like B goes to C. If B also goes to C, it's it's not so, sorry, it's another tail. If C goes to A, it's tail-to-tail, right? But now, if A goes to C, it's head-to-tail, because if you draw a path from A to B, right? And when you pass C, you first look at a head, and then you look at tail. That's why it's called head-to-tail. In this case, we can draw the same conclusion as the tail-to-tail structure. That is, condition on nothing. That means if you have to marginalize a C, right? Condition on nothing, A and B are not independent. However, condition on C itself, if C is given, C is observed, then A and B are independent. Right? I will leave you as an exercise to check why this is true. You can just follow the same analysis as we did, and it's very straightforward to verify this fact. Okay, let's stop here today and see you on next Tuesday.